Hello, and welcome. Tonight, we're going to watch water work. Not the dramatic, violent work of floods and storms, but the patient, a persistent work that happens over thousands and millions of years. The work of rivers. Rivers are sculptors. They carve landscapes with nothing more than flowing water, gravity, and time. Endless time. They create valleys and canyons, build plains and deltas, shape entire continents. And they do all of this slowly, so slowly that in a human lifetime, we barely notice the change. But the change is always happening. Right now, at this very moment, every river on Earth is carrying away tiny particles of rock and soil, moving them downstream, reshaping the land, grain by grain, day by day, century by century. Tonight, we're going to slow down time even further. We're going to watch a river system evolve from its very beginning to its mature form. We'll see how water creates the landscape around us, how it has created the landscape for hundreds of millions of years, how it will continue to create landscape long after we're gone. So settle in, get comfortable. Let the gentle sound of flowing water carry you through this journey. And let's begin at the very beginning, with a single drop of water falling on bare rock. Imagine a landscape that has just been born. Perhaps it's a volcanic island, risen from the ocean floor through millions of years of eruptions, finally tall enough to break the surface. Or perhaps it's a mountain range, pushed up by the collision of continental plates, fresh rock exposed to the sky for the first time. The rock is bare. No soil yet, no plants, just stone, hard and seemingly eternal. But stone, despite its hardness, is not permanent. Nothing is permanent. Everything changes, given enough time. Rain falls on this bare rock. It's been falling here ever since the land rose above sea level, but at first, there was nowhere for it to go but back to the ocean. The rock surface was smooth, or at least smoother than it is now. The water ran off in thin sheets, spreading across the surface, finding the easiest path downhill. But even then, the work began. Even then, the water was starting to shape the land. Water is not just water. Pure water would be relatively harmless to rock, but rainwater is never pure. As it falls through the atmosphere, it dissolves carbon dioxide, forming weak carbonic acid. This is the same acid that makes carbonated beverages fizzy. But in rainwater, it's dilute, gentle, yet it's enough. When this slightly acidic water touches certain types of rock, particularly limestone, marble, or any rock containing calcium carbonate, a chemical reaction begins. The carbonic acid reacts with the calcium carbonate, dissolving it, breaking it down into ions that can be carried away by the water. This process is called chemical weathering, and it happens slowly, incredibly slowly. A single raindrop dissolves an amount of rock far too small to measure, but billions of raindrops, falling over thousands of years, dissolve enough rock to notice. Over millions of years, they can dissolve entire mountain ranges. But chemical weathering is just one process. There's also physical weathering, and this happens even to rocks that don't dissolve in acid. Water seeps into cracks in the rock. This happens naturally. Even the hardest, most solid-looking rock has microscopic cracks and fissures. Water enters these cracks, trickles down into them, fills them. Then, when the temperature drops below freezing, something remarkable happens. Water expands when it freezes. It's one of water's unique properties. Most substances contract when they solidify, but water does the opposite. It expands by about 9%. This expansion creates tremendous force. Water freezing in a crack can exert pressures of up to 30,000 pounds per square inch. This is enough to split rock. The crack widens, just slightly. Next time it rains, more water enters the widened crack. Next time it freezes, the crack widens more. Freeze and thaw, over and over, perhaps hundreds of times per year in climates with regular freeze-thaw cycles. Over decades and centuries, the crack grows. Eventually, a piece of rock breaks free, tumbles down the slope. Now there are two things on the landscape: solid bedrock and loose rock fragments. And this changes everything. The rock fragments that break off don't stay where they fall. The next rain carries them down slope, even if only a few inches. They tumble, roll, slide. And as they move, they bump against the bedrock and against each other. Each collision chips away a tiny fragment. The rocks become smaller, smoother. They're being broken down, worn away. This process is called abrasion, and it's how rivers do much of their work. But we're not at a river yet. We're still at the very beginning, with water running over bare rock in thin sheets, carrying tiny rock fragments downslope. The fragments are sand-sized now, some even smaller, silt and clay particles, microscopic but countless. These particles settle in low spots, in depressions in the rock. Over time, these low spots fill with sediment. The sediment holds water, stays moist, even between rainstorms. And eventually, something miraculous happens. Life takes hold. A spore lands in a damp hollow filled with sediment. It germinates. A tiny plant, perhaps a moss or a lichen, begins to grow. This plant is a pioneer, one of the first living things to colonize this bare rock landscape. The plant survives on almost nothing. Water when it rains. Nutrients dissolved from the rock by acidic water. Sunlight. Carbon dioxide from the air. It grows slowly, spreads slowly, but it grows. And in growing, it changes everything. The plant's roots, tiny as they are, grow into cracks in the rock, widening them further. When the plant dies, its remains add organic matter to the sediment. This organic matter holds more water, provides more nutrients for the next generation of plants. More plants arrive. More sediment accumulates. The depressions in the rock become filled with primitive soil. And now, when rain falls, the water doesn't run off as easily. Some of it soaks into this soil, is held there, released slowly over time. But not all of it. Some water still runs off, still flows downslope. And this water follows the same paths every time. The paths of steepest descent, the low spots, the places where bedrock has been worn slightly deeper than the surrounding surface. These paths are the ancestors of rivers. They're not rivers yet. They're just threads of water, appearing during rainstorms, disappearing when the rain stops. But they're there, in the same places, doing the same work, every time it rains. Where water flows repeatedly, it carves slightly deeper into the rock. The process is invisible at the human timescale. You could watch one of these flow paths for your entire life and never see it get deeper. But over centuries, over millennia, the deepening becomes measurable. The deepening is uneven. Some parts of the bedrock are harder than others. Different minerals have different resistance to erosion. Where the rock is softer, the water cuts deeper. Where the rock is harder, erosion is slower. And these areas become small waterfalls or rapids. But even hard rock erodes eventually. The waterfalls migrate slowly upstream as the water undercuts the hard layer, causing chunks to break off. The rapids gradually smooth out as the hard spots are worn down. After 10,000 years, the flow paths have become channels. They're only a few inches deep, perhaps a foot wide, but they're distinct features in the landscape. During rainstorms, water flows in these channels, gurgling over stones, carrying sediment downslope. Between rainstorms, the channels are dry, or almost dry. Some water remains in pools, in the deeper spots, but there's no continuous flow. Not yet. The channels don't exist in isolation. They're connected in a pattern, a network. Smaller channels merge into larger ones. The larger channels merge into still larger ones. All of them flowing downhill. All of them heading toward the same destination, the sea, or a lake, or some other body of water at a lower elevation. The area drained by this network of channels is called a watershed or catchment. Every point in the landscape drains toward one channel or another. Ridges between channels form the boundaries. Water falling on one side of the ridge flows one way, water falling on the other side flows another way. These ridges and channels define the fundamental shape of the landscape. They're forming naturally, automatically, as water responds to gravity and the shape of the bedrock beneath. No planning, no design, just water finding the path of least resistance. After 100,000 years, the pattern is clear. The landscape is no longer smooth bare rock. It's textured, carved into ridges and valleys, with a dendritic, tree-like pattern of channels spreading across its surface. And now, something new begins. The channels become deeper, the watershed becomes more established, the soil thickens and retains more water. The conditions are right for the next stage, the birth of a permanent stream. It happens gradually. Perhaps there's a spring where groundwater seeps out from between rock layers. Or perhaps the soil has become thick enough to act as a reservoir, releasing water slowly and continuously rather than all at once. Or perhaps the climate becomes wetter, with more frequent rainfall. Whatever the cause, one day, though day is misleading, because this transition takes decades or centuries. There's water flowing in one of the channels, even when it hasn't rained recently. Not much water, a trickle, barely enough to cover the channel bed. But it's there, flowing constantly, day and night. This is the birth of a stream. And once a stream exists, once there's permanent flowing water, the rate of erosion increases dramatically. Flowing water can move more sediment than rainwater, running off in sheets. Flowing water can carve deeper channels, can transport larger particles, can reshape the landscape more quickly. After 1 million years, our landscape has been transformed. Where there was once bare rock, there's now a valley with a stream flowing through it. The valley is shallow, narrow, V-shaped. The stream is small, clear, cold, flowing swiftly over a rocky bed. Its banks are lined with plants, mosses, ferns, small shrubs, and the stream is connected to tributaries, smaller streams that flow into it from the sides. Each tributary has its own tiny valley, its own catchment. Together, they form a river system in miniature. But this is just the beginning. The stream will continue to change, to evolve, to shape the landscape. Over millions more years, it will become a mature river, creating landforms that will endure for millions of years after that. Let's follow this stream forward in time and watch how it grows. Our stream is young. In the language of geomorphology, the study of landforms, a young river has certain characteristics. It flows in a relatively straight path, following the steepest descent down the slope. Its channel is narrow and deep, cut into the bedrock with steep sides. It has a steep gradient. It drops elevation rapidly over its length. Young rivers are energetic. The water flows fast, tumbles over rocks, creates rapids and waterfalls. This energy allows the river to carry large amounts of sediment and even move large rocks downstream during floods. Let's examine these characteristics one by one, slowly, understanding how each one shapes the landscape. In its youth, our river flows almost straight down the slope. It hasn't had time to develop the meanders, the curves and loops that characterize older rivers. It's taking the most direct route from high elevation to low elevation. But even now, there are slight curves. Perhaps the river encountered a particularly hard layer of rock and had to flow around it. Perhaps a landslide partially blocked the channel, forcing the water to find a new path. These small deflections are the seeds of future meanders, but we'll come to that later. For now, the river flows straight, or nearly so. Its path is controlled by the bedrock beneath it and by the original slope of the land. The channel is narrow, perhaps only 10 or 20 feet wide, for a river that will eventually be hundreds of feet wide. The water is confined, concentrated, fast-moving. The primary work of a young river is downcutting, cutting deeper into the bedrock beneath it. Every rock, every grain of sand that the river carries acts as a tiny tool, abrading the channel bed as it moves downstream. During floods, when the river is flowing at its fastest and carrying the most sediment, the abrasion is most intense. But downcutting isn't just about abrasion. There's also a process called hydraulic action. Fast-moving water creates pressure differences that can pluck chunks of rock from the channel bed, especially if the rock is already fractured or weakened. The water forces its way into cracks, and when it's flowing fast enough, it can literally tear pieces of rock away. The rate of downcutting is slow by human standards, but rapid in geological time. A young river might cut downward at a rate of 1 millimeter per year in hard rock, faster in softer rock. That's 1 meter per 1,000 years, 1 kilometer per million years. Our river has been flowing for about 2 million years now. It's cut down perhaps 2 kilometers below its original channel, 2 kilometers of rock, eroded and carried away. grain by grain, to the sea. As the river cuts down, the valley walls don't stay vertical. They can't. Rock isn't strong enough to support vertical cliffs thousands of feet high, at least not for long in geological terms. The walls collapse, slump, erode. Gravity pulls rocks and soil down the valley walls. Rain washes sediment downslope. Small streams, tributaries, cut their own channels into the valley walls, creating a complex network of gullies and ravines. The result is a V-shaped valley, narrow at the bottom where the river flows, wider at the top, with sloping walls. The angle of the slopes depends on the rock type and climate, but it's typically between 30 and 60 degrees. From above, the valley looks like a V carved into the landscape. The river at the bottom is a thin line, sometimes visible, sometimes hidden by vegetation along its banks. The V is the signature of a young river, the mark of active downcutting. Our young river is not smooth. Its channel is interrupted by waterfalls and rapids, places where the water tumbles over rock ledges or flows rapidly through boulder-choked narrows. Waterfalls form where there are significant differences in rock hardness. Perhaps the river flows over a layer of hard granite underlain by softer shale. The shale erodes faster, undercutting the granite. Eventually, the unsupported granite collapses, and the waterfall migrates upstream, leaving behind a deep pool called a plunge pool. Let's pause here and watch a waterfall for a while. It's worth understanding how it works, how it slowly destroys itself and migrates upstream. The water falls 20 feet from the granite ledge into the plunge pool below. The force of the falling water, combined with the rocks and sediment it carries, scours the pool deeper. The swirling water and tumbling rocks act like a drill, boring into the softer shale beneath the granite. As the plunge pool deepens, it undercuts the granite ledge. The granite projects out over empty space, unsupported. Cracks develop in the granite, weakened by the constant vibration from the falling water and by freeze-thaw cycles. Eventually, and this might take decades or centuries, a chunk of granite breaks off and crashes into the pool below. Now the waterfall is a foot or two further upstream. The process begins again. The falling water excavates the pool, undercuts the ledge collapses. Over thousands of years, the waterfall slowly migrates upstream, leaving behind a gorge, a steep-walled canyon marking its former positions. Niagara Falls, one of Earth's most famous waterfalls, has migrated upstream about 7 miles over the past 12,000 years, since the end of the last ice age. That's an average of about 1 foot per year, though the rate varies. In human history, the falls have moved about 300 feet upstream, enough to be noticeable in old photographs compared to today. Our river's waterfalls are doing the same thing, on the same timescale. They're temporary features, lasting only thousands or tens of thousands of years before migrating upstream and eventually being smoothed away entirely as the river establishes a more uniform gradient. Gradient means slope. Specifically, the change in elevation per unit of distance. A young river typically has a steep gradient, dropping elevation rapidly. Our river might drop 50 feet per mile, or even more in its upper reaches. This steep gradient gives the river its speed and energy. The water flows fast, perhaps 5 or 10 miles per hour in the main channel, faster in rapids. This speed allows the river to carry large particles and lots of sediment. There's a relationship between gradient, velocity, and sediment size that's fundamental to understanding rivers. Fast-flowing water can carry larger particles than slow-flowing water. Very roughly, water flowing at 1 foot per second can move fine sand. Water flowing at 2 feet per second can move coarse sand and fine gravel buffer. Water flowing at 3 feet per second can move gravel and small pebbles. Water flowing at 5 feet per second can move cobbles kind of process. Water flowing at 10 feet per second can move boulders. Our young river, flowing fast down its steep gradient, has enough energy to move substantial rocks, especially during floods when the water level rises and the velocity increases. The river we're watching doesn't maintain a constant flow. During dry periods, the water level drops and the river becomes a modest stream, flowing peacefully through its channel. But during wet periods, during prolonged rains or snowmelt, the water level rises dramatically. A flood is defined as when a river overflows its banks. But in a young river with steep valley walls, there are no floodplains to overflow onto. Instead, the water simply rises within the confines of the V-shaped valley, rushing down the steep channel with tremendous velocity. These floods are when most of the river's erosional work happens. The higher water level means higher velocity, which means ability to move much larger rocks. A flood might last only a few days or weeks, but it can move more sediment than decades of normal flow. Boulders that have been immobile for years suddenly begin to move. They tumble downstream, colliding with other rocks, with the channel bed. Each collision chips away fragments, gradually making the boulders smaller, rounder, smoother. Eventually, they'll be reduced to cobbles, then gravel, then sand, then silt, then clay, each step taking centuries or millennia. After the flood passes, these transported rocks come to rest somewhere downstream. The largest ones stop moving first, as soon as the water velocity drops below the threshold needed to move them. Smaller rocks move further. The smallest particles, silt and clay, remain suspended in the water and are carried all the way to the ocean. This sorting of sediment by size is one of the fundamental processes in rivers. It creates patterns we can see and measure, patterns that geologists use to interpret how rivers behaved in the past. If we could slice through the landscape vertically, following the river from its headwaters to its mouth, we'd see the river's longitudinal profile, a cross-section showing how its elevation changes along its length. A young river's profile is steep and irregular. There are sudden drops where waterfalls exist, flat sections in pools between rapids, and a general steep descent toward base level, the lowest elevation the river can reach, usually sea level or the level of the lake or larger river it flows into. Over time, this profile will become smoother, more curved, approaching what geologists call a graded profile. But that will take millions of years. For now, the profile is rough, irregular, still being shaped by the river's energetic downcutting. Our river isn't alone in its valley. It's fed by tributaries, smaller streams that flow into it from the sides. Each tributary has its own valley, its own watershed, its own work of erosion. The pattern of these tributaries, seen from above, is dendritic, tree-like, with smaller branches joining larger branches, ultimately merging into a trunk. This pattern emerges naturally when rivers develop on relatively uniform rock with no strong structural control. In other landscapes, with different geological structures, rivers form different patterns. Trellis patterns develop where there are alternating bands of hard and soft rock. Radial patterns develop on volcanic cones or domes. Rectangular patterns develop where joints or faults control the river courses. But our river is developing a dendritic pattern, the most common pattern on Earth. Each tributary is itself a young river, cutting its own V-shaped valley, forming its own waterfalls and rapids. The whole watershed is a network of active erosion, with water cutting deeper and deeper into the landscape. But this erosion can't continue forever. There's a limit, called base level. For most rivers, base level is sea level. A river can't cut deeper than the level of the body of water it flows into, because once it reaches that level, it has no gradient left, no slope to drive the flow. Our young river is cutting down toward base level, but it hasn't reached it yet. Its mouth, where it enters the sea or a lake, is at base level. But upstream, it's still well above base level, still cutting down, still doing the work of erosion. The concept of base level is important because it controls the ultimate shape the river system will achieve. Everything the river does, every meander it forms, every floodplain it creates, is influenced by its elevation relative to base level, and base level itself can change. If sea level rises, base level rises, and the river deposits sediment, building up its channel. If sea level falls, base level falls, and the river cuts down more vigorously. During Earth's ice ages, when much water was locked up in glaciers, sea level was hundreds of feet lower than today. Rivers cut deep valleys in response. When the ice melted and sea level rose, those valleys were flooded, creating the drowned river valleys we now call estuaries. Our river will experience these changes over millions of years. But for now, It's in its youth, cutting down vigorously, shaping the landscape with patient, persistent erosion. Let's move forward in time now, watching as our young river matures. Time passes. 5 million years. 10 million years. The river continues its work, never stopping, never resting, and gradually, the landscape changes. The river has cut down closer to base level. Its gradient, its slope, is less steep now. In its upper reaches, it still flows swiftly, still has waterfalls and rapids, but in its middle and lower reaches, the gradient has decreased. The river flows more slowly, more gently. This change in gradient marks the transition from youth to maturity. A mature river has different characteristics than a young one. Different energy, different work to do, different landforms to create. When a river is young and steep, most of its energy goes into down-cutting, eroding the channel bed and cutting deeper into the bedrock. But as the gradient decreases and the river approaches base level, less energy is available for down-cutting. The river can't cut much deeper because it's approaching the limit imposed by base level, so the river's energy goes elsewhere. Instead of cutting down, it begins to cut sideways, a process called lateral erosion. The river begins to widen its valley, to swing from side to side within the valley it has created. This is the beginning of meander development, one of the most beautiful and mathematically elegant processes in geology. Let's slow down and watch it happen. Even a young river flowing in a straight channel has slight irregularities. Perhaps there's a boulder on one side of the channel. Water flowing past the boulder speeds up slightly as it's constricted. This faster water has more erosive power, so it cuts into the bank slightly. Now there's a small indent in the bank. Water naturally tends to flow into indents, creating a slight curve in the flow. And once there's a curve, the physics of flowing water creates a self-reinforcing feedback that makes the curve grow larger. On the outside of a curve, the outer bank, water flows faster, and the channel is deeper. The faster flow has more energy, more erosive power. It undercuts the bank, causing soil and rock to collapse into the river. The curve becomes more pronounced. On the inside of the curve, the inner bank, water flows slower, and the channel is shallower. The slower water deposits some of its sediment load. A point bar begins to form, a gently sloping deposit of sand and gravel on the inside of the bend. So the outside bank erodes, while the inside bank accumulates sediment. The channel stays roughly the same width, but it migrates sideways. The curve becomes more pronounced. A gentle bend becomes a pronounced curve, which becomes a loop, which might eventually become so extreme that the river cuts through the neck of the loop and abandons the extreme curve entirely. This is how meanders form. And once they start to form, they continue to grow and migrate, creating some of the most distinctive landforms in river systems. After a few 100,000 years of this process, our river no longer flows in a relatively straight path. Instead, it winds back and forth across its valley in a series of smooth, sinuous curves, meanders. The meanders aren't random. They follow mathematical patterns that are remarkably consistent across different rivers, different continents, even different planets. The wavelength of meanders, the distance from one curve to the next, is typically 10 to 14 times the width of the channel. The radius of curvature, how tight the curves are, is typically 2 to 3 times the channel width. These ratios emerge naturally from the physics of flowing water. They're not designed or planned. They're simply the stable configuration that water naturally assumes when flowing through sediment. It can erode and deposit. From above, a meandering river looks like a snake, winding back and forth across the landscape. The curves are smooth, elegant, beautiful. Native Americans sometimes described rivers as snakes for this very reason. And indeed, meanders and snakes follow similar mathematical patterns. Both are optimizing for efficient movement through their respective mediums. Meanders don't stay in one place. They migrate, slowly and continuously, in two directions, downstream and laterally across the valley. The downstream migration happens because erosion on the outside of a curve is usually strongest, slightly downstream of the apex of the curve, while deposition on the inside happens slightly downstream as well. The result is that the entire curve shifts gradually downstream, like a wave moving through the river channel. The lateral migration happens as the river erodes one bank and deposits on the other. The meanders swing back and forth across the valley like a pendulum, though on a timescale of thousands of years. The rate of migration varies enormously depending on the rock type and climate. A river flowing through soft sediment might migrate hundreds of feet per year. A river flowing through bedrock might migrate only inches per century. Our river, flowing through a mix of sediment and rock, migrates at an intermediate rate, perhaps 10 or 20 feet per year on average. Over millennia, this migration erases the V-shaped valley the river carved in its youth. The valley becomes wider, flatter. The river swings from one valley wall to the other, eroding the bases of the walls, causing them to retreat. Eventually, the valley becomes wide enough that the river has room to meander freely without touching the valley walls at all. The flat area on either side of a meandering river is called the floodplain. It's called this because it floods. When the river overflows its banks during high water, the floodplain is covered with water. But the floodplain is also a depositional feature, built by the river over thousands of years. Every time the river floods, it deposits a thin layer of sediment on the floodplain, silt and fine sand carried in suspension by the floodwater. Over time, these layers accumulate, building up the floodplain elevation. The floodplain is also built by the migration of meanders. As a meander migrates laterally, it erodes sediment from the outer bank and deposits it on the inner bank. Over time, as the meander swings back and forth, it deposits a layer of sediment across the entire width of its migration path. These deposits, called point bar deposits, form much of the floodplain's substance. After 1 million years or so, our river has created a substantial floodplain, perhaps half a mile wide on either side of the channel. The floodplain is nearly flat, covered with sediment deposited by the river. During normal flow, the river occupies only a small channel within the floodplain. During floods, water spreads across the entire floodplain, turning it into a shallow lake. Sometimes, a meander becomes so extreme that the river takes a shortcut. The neck of the meander, the narrow strip of land separating one part of the curve from another, is eroded through during a flood. The river adopts the shorter, steeper path through the cutoff, abandoning the old curved channel. The abandoned curve becomes isolated from the main river. It's still filled with water, a crescent-shaped lake, called an oxbow lake, named for its resemblance to the U-shaped piece of wood that goes around an ox's neck in a yoke. Oxbow lakes are common features on the floodplains of mature rivers. They're temporary, though, gradually filling with sediment, being colonized by aquatic plants, slowly transforming into wetlands, and eventually into dry land. But this process takes centuries or millennia, and new oxbow lakes are being created as fast as old ones are filling in. From the air, a mature river's floodplain is marked by numerous crescent-shaped lakes and wetlands, showing the former positions of meanders. They're a record of the river's history, a map of where it used to flow. During floods, when water overflows the banks of the main channel, something interesting happens. The water velocity decreases dramatically as soon as it spreads out over the floodplain. And when velocity decreases, sediment is deposited. The coarsest sediment, sand, is deposited first, right at the channel edge. Over many floods, this builds up into natural levees, low ridges of sand running parallel to the channel on both sides. Natural levees are typically only a few feet high, but they're significant. They make it harder for the river to overflow its banks. Once water overtops the levees, it spills onto the floodplain, but it takes a higher water level to reach that point. Natural levees also create a distinctive topography on the floodplain. The highest ground is right next to the river, along the levees. Further from the river, the floodplain is lower. These areas are called backswamps because water that floods onto the plain accumulates there and is slow to drain back to the river. This might seem counterintuitive. We tend to think of land near rivers as low-lying and flood-prone, which it is, but the immediate riverbank is actually higher than the surrounding floodplain because of levee deposition. As the river matures, the character of its sediment load changes. In its youth, the river carried boulders and cobbles, tumbling them along its steep, rocky bed. Now, with a gentler gradient, it carries mostly sand, silt, and clay. The larger particles have been left behind upstream, deposited where the gradient decreased and the river no longer had enough energy to move them, or they've been broken down into smaller particles by the continuous grinding and collision that happens during transport. The mature river is still doing erosional work, but it's different work. Instead of deepening its valley, it's widening it. Instead of moving boulders, it's moving fine sediment. Instead of cutting bedrock, it's reworking the sediment of its own floodplain. During floods, the river erodes material from the outer banks of meanders and deposits it on the inner banks or across the floodplain. Between floods, it flows peacefully through its channel, a muddy brown or green color from all the suspended sediment it carries. The mature river landscape. Let's step back and look at what we've created. The landscape has been transformed from the V-shaped valley of the young river to something entirely different. The valley is now wide and flat-bottomed. The river meanders across this flat floor, confined to a channel perhaps 100 feet wide, but with the freedom to migrate across a floodplain a mile or more wide. The valley walls still exist, but they're far from the river now, eroded back over millions of years. The floodplain is dotted with oxbow lakes, wetlands, and abandoned channels. Natural levees line the river channel. Tributaries join the main river, each one bringing water and sediment from its own drainage basin. This is a mature river in its prime. It's still changing, still doing geologic work, but the character of that work has shifted from downcutting to lateral migration and floodplain building. And yet, this isn't the end of the river's evolution. There's one more stage to come, a stage where the river's energy decreases further and its behavior changes again. This is old age, and it creates some of the most extensive and distinctive landforms on Earth. But before we reach old age, let's pause and consider some of the extraordinary examples of mature rivers on Earth today. The Mississippi River, in its middle and lower reaches, is a classic mature river. It meanders across a floodplain up to 80 miles wide in places. Its meanders migrate at rates measured in tens of feet per year. It's cut off so many meanders over the centuries that its floodplain is littered with oxbow lakes. The Amazon River, the world's largest river by volume, shows similar patterns. Its main stem meanders sedately across a vast floodplain built over millions of years. During the annual flood season, much of this floodplain is inundated, creating a flooded forest ecosystem unlike any other on Earth. The Ganges River in India, sacred to millions of Hindus, flows through one of the world's most densely populated floodplains. The river has changed course multiple times in recorded history, abandoning old channels and carving new ones. This is normal behavior for a mature river, though it's challenging for the people who live along its banks. These great rivers show us what our hypothetical river will eventually become, given enough time, enough erosion, enough sediment transport. They're not the end point of river evolution, but they're close. Let's watch as our river continues to evolve, approaching the final stage of its development. More time passes, the river continues its work. It continues to erode, transport sediment, deposit that sediment elsewhere. The landscape continues to change, though the changes are becoming more subtle. The river has now cut down almost to base level along most of its length. Its gradient, its slope, is very gentle. In its lower reaches, it might drop only a few inches per mile. At this gradient, the river has very little energy for erosion. It flows slowly, lazily, making broad loops across an extensive floodplain. This is old age in river terminology. An old river has different characteristics than a young or mature river. It's less about erosion now, and more about transportation and deposition. The river is moving sediment from upstream to downstream, but it's not cutting deeper into the landscape. It's reached an equilibrium, a balance. An old river meanders even more extensively than a mature river. The curves are broader, more exaggerated. The river might loop back on itself so extensively that it flows north for a while, then south, then north again, all while its overall direction of flow is east. The distance the river travels is many times the straight line distance from source to mouth. This excessive meandering is possible because the river has so little energy. It can't maintain a straight course. Any slight deflection grows into a meander, and the meanders grow until they're extreme. The river is taking the path of least resistance, which, paradoxically, is not the shortest path, but the most meandering one. The floodplain is now very wide, sometimes tens of miles from one valley wall to the other. During major floods, which might occur once every decade or century, the entire floodplain is submerged. These are the great floods of history, the ones that make the news, the ones that affect millions of people. But they're normal events in the life of a river, events that have been happening regularly for millions of years. Between floods, the river flows peacefully through its channel. The water is murky, with suspended sediment, clay, and silt particles so fine they stay suspended almost indefinitely. The river appears brown, grey, or yellowish, depending on the color of the sediment it's carrying. Fish swim in this murky water, catfish and other species adapted to low visibility. Birds wade in the shallow edges, hunting for food. Trees grow on the natural levees and on the higher parts of the floodplain. Wetlands fill the backswamps. The river and its floodplain form a complex ecosystem, home to countless species. As our river approaches the ocean or lake it drains into, the gradient becomes even gentler. The river is barely above base level now. The flow is slow, the meanders extreme, the floodplain wide and flat. And then, finally, the river reaches base level. It arrives at the coast. And here, something new happens. The river enters a body of standing water, the ocean, a sea, a large lake, and its flow suddenly stops. When flowing water enters standing water, it deposits its sediment load, all of it. The coarsest particles settle out first, then progressively finer particles as the water spreads out and slows further. The finest clay particles might remain suspended for days, gradually settling to the bottom far from shore. This deposition creates one of the most distinctive landforms in all of geology, a delta. Let's slow down and watch how a delta forms. It's a process that takes thousands of years to see clearly, but we can speed up time in our minds, watch the delta grow and evolve. The river emerges from the land and flows into the sea. At the river mouth, the fresh river water is less dense than the salty seawater. It tends to float on top of the seawater, spreading out as a plume of turbid, sediment-laden water. As this plume spreads and slows, sediment settles out. The coarsest sand settles right at the river mouth, forming a bar, a raised area of sediment just offshore. Over time, this bar builds upward until it breaks the surface, becoming dry land. The river now encounters this bar, blocking its path. Water flows around it, finding the easiest routes on either side. The single channel splits into two distributaries, branches that distribute the river's flow. Each distributary builds its own bar at its mouth. Each bar grows until it breaks the surface. Each bar causes the flow to split again. The result is a branching network of distributaries, all of them spreading the river's water and sediment across a broad area of the coast. This is a delta, named after the Greek letter delta delta, which has a triangular shape like some deltas when viewed from above. Though not all deltas are triangular, some are bird's foot shaped, some are arcuate, some are irregular. The shape depends on the balance between river deposition, wave action, and tides. Let's look at different types of deltas and understand what creates each type. A river-dominated delta forms when the river is carrying a large sediment load and the ocean has weak waves and tides. The river deposits its sediment faster than waves, and currents can redistribute it. The result is a delta that extends far out into the ocean, with long distributary channels extending like fingers. The Mississippi River Delta is a classic example of this type. Specifically, it's called a bird foot delta because the distributaries look like the toes of a bird's foot when seen from above. A wave-dominated delta forms when waves are strong enough to rework the sediment of the river deposits. Instead of finger-like distributaries, the sediment is spread along the coast by waves, forming broad beaches and barrier islands. The delta is more rounded, arcuate. The Nile Delta is an example of this type, though human activities have modified it significantly. A tide-dominated delta forms where tidal currents are strong. The tides carry sediment up and down tidal channels, creating a complex network of channels and tidal flats. The Ganges-Brahmaputra Delta is partially tide-dominated, with extensive tidal forests called the Sundarbans. Our river is creating a river-dominated delta. The waves and tides where it enters the ocean are relatively weak, so the river controls the delta's shape. Distributaries extend outward, building new land, advancing the coastline seaward. The delta grows steadily, inexorably. Every year, the river delivers millions of tons of sediment to the delta. This sediment is deposited in the distributary channels, on the delta front, and on the delta plain, the flat land behind the active distributaries. The delta plain is barely above sea level, prone to flooding during storms or spring tides. It's a wetland environment, with marshes, swamps, and shallow lakes. Vegetation colonizes it: marsh grasses, reeds, mangroves in tropical climates. These plants stabilize the sediment, trap more sediment with their roots and stems, help build the delta upward as well as outward. Over thousands of years, the delta extends miles into the ocean. Where there was once open water, there's now land, new land, created by the river. This is the river's ultimate work, the culmination of its millions of years of erosion upstream. All that material carved from mountains, transported down rivers, is now rebuilding the land here at the coast. Delta, switching. But deltas are dynamic, ever-changing. A river flowing across its delta seeks the shortest, steepest path to the ocean. As the delta builds outward in one direction, other paths to the ocean become shorter and steeper. Eventually, during a major flood, the river might break through a natural levee and adopt a new, shorter course to the ocean. It abandons its old distributary network and creates a new one. This process is called delta switching or avulsion. The abandoned part of the delta is no longer receiving sediment. Without continued sediment supply to maintain it, it begins to subside, to sink. The land compacts under its own weight. Organic material in the soil decomposes and shrinks. Sea level rise, always occurring on geological timescales, drowns the abandoned delta. Over time, the abandoned delta becomes a submerged platform offshore, while the active delta builds outward in a new direction. Then, centuries or millennia later, the river switches again, perhaps returning to an old channel, perhaps creating an entirely new one. The result is that a mature delta is composed of multiple overlapping delta lobes, each representing a different phase of delta growth. The Mississippi Delta has at least 6 major lobes built over the past 7,000 years. The modern Birdfoot Delta is just the most recent. Deltas are among the most productive ecosystems on Earth. They're rich in nutrients, washed down from the entire watershed. They're diverse, with freshwater, brackish water, and saltwater environments all close together. They're dynamic, constantly changing, creating new habitats as they grow and evolve. They're also vulnerable. Deltas are low-lying, flood-prone, subject to storms and tsunamis. The land is unstable, subsiding, shifting. Yet millions of people live on deltas worldwide. The Nile, the Mississippi, the Ganges-Brahmaputra, the Mekong, the Yangtze. These river mouths are attractive because the soil is fertile, water is abundant, and access to both river and ocean enables trade and transportation. Our hypothetical river's delta is uninhabited by humans. Humans don't exist yet in our timeline, or at least not here, but it's teeming with other life. Birds nest in the marshes, fish spawn in the shallow waters, crabs and shrimp inhabit the tidal channels. It's a vibrant, living landscape, built entirely by the patient work of flowing water. And so we reach the end of our river's journey. The sediment eroded from mountains millions of years ago and hundreds or thousands of miles upstream has finally come to rest. It's been deposited on the delta, layer upon layer, building new land. But even here, the story doesn't end. The sediment on the delta will continue to accumulate, building up layers hundreds or thousands of feet thick over millions of years. Eventually, these layers will be buried deep enough to be compressed into sedimentary rock, sandstone, shale, limestone. The rock will preserve the shape of the old river channels, the texture of the sediment, even fossils of the organisms that lived on the delta. Millions of years later, If the sea level falls or the land is uplifted by tectonic forces, this sedimentary rock might be exposed at the surface again. Erosion will begin, rain will fall, new rivers will form, and they might cut through the old sedimentary layers, revealing the ancient delta's structure. The cycle continues. Rock is eroded, sediment is transported, new rock is formed. Rivers create landscapes. Those landscapes are buried and become rock. New rivers erode that rock. The cycle has been happening for billions of years. Since Earth first had liquid water on its surface, it will continue for billions more, until the sun's increasing brightness eventually evaporates Earth's oceans entirely. We've traced the evolution of a single river system from bare rock to mature delta. But not all rivers follow this exact path. There are variations, special cases, rivers that behave differently because of their particular circumstances. Let's explore some of these variations. They'll help us understand the diversity of river systems on Earth and the many ways that water shapes landscapes. Some rivers, instead of meandering, split into multiple channels that braid together like strands of hair. These braided rivers have a distinctive appearance from the air. Multiple channels separated by bars and islands, constantly shifting and rearranging. Braided rivers form under specific conditions. They need a high sediment load, more sediment than the river can transport efficiently. They need erodible banks. If the banks are too stable, the river can't create new channels. And they often have highly variable flow, with dramatic differences between floods and low water. When these conditions exist, here's what happens. The river deposits sediment in its channel, forming bars. During low flow, these bars divide the flow into multiple threads. During high flow, the threads shift, erode new channels, abandon old ones. The result is a constantly changing braided pattern. Braided rivers are common in glacial environments, where glacial meltwater carries huge amounts of sediment. They're also common in semi-arid environments, with seasonal flash floods. The Brahmaputra River in Tibet and India is one of the world's largest braided rivers. From space, it looks like a shimmering web of water spread across a wide valley. Some rivers never develop extensive floodplains or deltas. They flow through canyons, their channels cut directly into bedrock, with little or no sediment on the channel floor. These are bedrock rivers, and they remain young throughout their existence. They form in areas where rock uplift is rapid, where tectonic forces are lifting the land faster than the river can cut down to base level. The river is constantly trying to reach equilibrium, but the ground beneath it keeps rising, keeping it perpetually steep and energetic. The Colorado River in the Grand Canyon is a bedrock river. It's cut down more than a mile through layers of sedimentary rock, but it hasn't reached base level because the Colorado Plateau is still being uplifted. The river is running in place, maintaining its steep gradient, even though it's been flowing for millions of years. Bedrock rivers can cut spectacular canyons. The erosion is slow but focused, carving narrow gorges through solid rock. The Grand Canyon took roughly 6 million years to form, fast in geological terms, but imperceptibly slow in human terms. In arid and semi-arid regions, where steep mountain streams emerge onto flat desert floors, they create a distinctive landform called an alluvial fan. Here's how it forms. The stream flows down a steep mountain valley, carrying cobbles and gravel. When it reaches the base of the mountains and the slope suddenly decreases, the stream loses energy and deposits its load. The coarsest material is deposited first, then progressively finer material further from the mountain front. During different floods, the stream takes slightly different paths, spreading sediment across a fan-shaped area. Over time, these deposits build up into a gently sloping fan of sediment, spreading out from the mouth of the mountain valley. Alluvial fans are common in the Basin and Range province of western North America, where steep mountain ranges are separated by flat desert basins. Death Valley is partially ringed by alluvial fans. They're also common at the edges of the Himalayas and other young mountain ranges. Not all rivers flow on the surface. In areas with soluble rock, especially limestone, rivers can disappear underground, flowing through caves and tunnels dissolved in the bedrock. This process starts when slightly acidic rainwater seeps into cracks in limestone. The acid dissolves the limestone, widening the cracks into caves. If a surface stream encounters one of these cave systems, it might flow into it and disappear underground. The underground river continues to dissolve limestone, enlarging its passages. It might flow underground for miles before emerging at a spring lower in the valley, or it might feed directly into the groundwater system, recharging aquifers. Mammoth Cave in Kentucky contains an underground river system that has dissolved more than 400 miles of passages through limestone. It's the longest known cave system in the world, and it's still actively enlarging as the underground river continues its work. Sometimes a river is older than the mountains it flows through. This seems paradoxical. How can a river cut through mountains? The answer is that the mountains rose slowly, while the river was already there. As the land uplifted, the river cut down at the same rate, maintaining its course. The river anteceded, came before, the mountains, hence the term antecedent river. This requires specific conditions. The uplift must be slow enough for the river to keep pace. If the uplift is too rapid, the river will be diverted around the rising mountains. But if the timing is right, the river will cut a deep gorge directly through the mountain range. The Columbia River, cutting through the Cascade Range, is thought to be antecedent. The river was flowing west from the Rocky Mountains when volcanic activity began building the Cascades. The river maintained its course, cutting through the volcanic rocks as they accumulated. Over very long timescales, tens or hundreds of millions of years, river valleys can become ridges. This seemingly impossible transformation happens when the river deposits resistant material in its channel, then stops flowing, and the landscape around it erodes away. Here's how. A river flowing through soft rock deposits gravel in its channel. The gravel is harder and more resistant to erosion than the surrounding soft rock. The river later shifts course or dries up. Erosion lowers the surrounding landscape, but the gravel-filled former channel erodes more slowly. Eventually, what was the lowest point, the valley floor, becomes the highest point, a ridge of gravel standing above the eroded landscape. This is called inverted relief or channel inversion. It's relatively common in areas with alternating layers of hard and soft rock, and with changing climate patterns that cause rivers to shift course. Not all rivers flow year-round. In arid and semi-arid climates, many rivers are ephemeral. They flow only after rainstorms, remaining dry the rest of the year. These rivers still shape the landscape. Each flow event transports sediment, erodes banks, deepens the channel slightly. Over thousands of years, ephemeral rivers create distinctive landforms, broad, flat, sandy washes in deserts, arroyos or wadis with steep banks. The paradox of ephemeral rivers is that they do geological work, very rarely, but very intensely. A single large flood might do more erosion and sediment transport than decades of dry weather. The channel sits empty most of the time, but when water does flow, it flows with tremendous power. Rivers, flowing from glaciers, have unique characteristics. The water is milky with suspended rock flour, fine sediment ground by the glacier from the bedrock beneath it. The discharge varies dramatically through the day, highest in the afternoon when glacial melting is most rapid, lowest at night when melting slows. Glacial rivers carry enormous sediment loads. This sediment is deposited when the river emerges from its mountain valley onto flatter ground, creating expansive outwash plains. These plains are often braided river systems, constantly shifting and rearranging channels across a bed of gravel and sand. Glacial rivers also transport icebergs, chunks of ice that break off from the glacier and float downstream. These icebergs carry embedded rocks and boulders, dropping them wherever the ice melts. This creates erratics, boulders found in locations far from their source rock. Where rivers meet the ocean, tides can influence flow for many miles upstream. In extreme cases, the lower portion of a river might actually flow backward during flood tide, with ocean water pushing upstream before being pushed back out to sea during ebb tide. The Hudson River in New York is tidal all the way to Troy, about 150 miles from the ocean. The Amazon is tidal for several hundred miles upstream. These tidal reaches are neither entirely river nor entirely ocean, but a hybrid, an estuary where fresh and salt water mix. Tidal rivers deposit distinctive sedimentary layers, with alternating bands of sediment deposited during flood and ebb tide. These rhythmites can be preserved in the geological record, providing evidence of ancient tidal rivers. We've watched a single river system evolve over millions of years. But let's step back further and take an even longer view. What happens over tens of millions of years? Hundreds of millions? Billions? Rivers have been shaping Earth's surface for as long as Earth has had liquid water and exposed land, more than 4 billion years. The rivers we see today are just the current iteration of a process that has been continuous, with occasional interruptions throughout Earth history. Rivers leave traces in the geological record. When sediment deposited by ancient rivers is buried and compressed into sedimentary rock, that rock preserves the structure of the river system that created it. Geologists can recognize ancient river channels in rock formations. The channels are filled with sandstone, compressed ancient sand, the shape of the channel, the pattern of the sand grains. Even the direction of ancient currents can be determined from the rock. Some ancient rivers were enormous, far larger than any river on Earth today. This is because Earth's continents have been arranged differently at different times in the past. When continents merge into supercontinents, the interior of the supercontinent is far from the ocean. Rivers draining this vast interior can grow to immense size before reaching the sea. There's evidence of ancient rivers in some of the oldest rocks on Earth, rocks more than 3 billion years old. These rivers flowed across landscapes that would be utterly alien to us, under skies with little or no oxygen, through a world where life was confined to microscopic forms in the oceans. But the processes were the same. Water flowed downhill. Erosion occurred. Sediment was transported and deposited. Rivers are not unique to Earth. Wherever liquid can flow across a surface under gravity, river-like features can form. Mars once had rivers. We can see their dry channels from orbit, branching networks of valleys cutting across the ancient Martian highlands. These rivers flowed billions of years ago, when Mars had a thicker atmosphere and liquid water on its surface. Now they're dry, preserved like fossils in the landscape. Titan, Saturn's largest moon, has rivers flowing right now. But these aren't water rivers. Titan is far too cold for liquid water. They're methane rivers, flowing through channels carved in water ice. The physics is the same, though the chemistry is different. Methane rain falls, runs downhill, creates channels, eventually reaches seas of liquid methane at low elevations. Even Venus might have had rivers once, billions of years ago, before its runaway greenhouse effect evaporated its oceans and created its hellish modern climate. If those ancient rivers existed, all evidence of them has been erased by subsequent volcanic resurfacing. The universality of river processes, appearing wherever liquid flows across solid surfaces, tells us something profound. River formation is not a quirk specific to Earth. It's a fundamental consequence of physics, of gravity, of the properties of fluids. If we find planets with liquid on their surfaces, we should expect to find rivers. Much of Earth's land surface is covered by sedimentary rock formed from compressed sediment, and much of that sediment was deposited by rivers. When we see layered rocks exposed in cliffs and canyon walls, we're seeing the preserved record of ancient environments. Sandstone, with cross-bedding, angled layers within the rock, indicates ancient sand dunes or river channels. The angle of the crossbeds shows the direction of the ancient wind or water current. Shale, compressed mud, often represents ancient floodplains or lake bottoms. The fine grain size tells us the water was calm, allowing clay particles to settle. Conglomerate, compressed gravel, represents ancient river channels where flow was fast enough to move cobbles and pebbles. By studying these rocks, geologists can reconstruct ancient river systems in remarkable detail. They can map where rivers flowed, what directions they traveled, how large they were, what the climate was like, even what plants and animals lived along their banks. Rivers don't just shape landscapes at local scales. They play a role in the evolution of entire continents. Rivers erode mountains, carrying sediment from high elevations to low. This sediment accumulates in basins, on continental margins, building up thick sequences of sedimentary rock. Over millions of years, these sediments can be kilometers thick. The weight of these sediments depresses the crust beneath them, creating even more accommodation space for future sediment. Meanwhile, the mountains being eroded are lightened, causing them to rise isostatically. floating upward like a boat as its cargo is removed. This creates a feedback loop. Mountains rise as they're eroded, maintaining their elevation even as material is removed from their peaks. The erosion continues as long as the mountains remain high. Eventually, tens or hundreds of millions of years later, the tectonic forces that created the mountains cease. The mountains stop rising, but erosion continues, inexorably wearing them down until only the roots remain, a rolling landscape of gentle hills composed of metamorphic rock that was once deep in the mountain range's core. The Appalachian Mountains are going through this process. They were once as high as the Himalayas, perhaps 300 million years ago. Rivers have been eroding them ever since. Now, they're gentle, ancient, worn down. Given another 100 million years, they'll be eroded almost flat. The patient, steady erosion we've been describing is occasionally punctuated by catastrophic events that reshape landscapes in days or weeks instead of millions of years. These are megafloods, floods so large that they're almost beyond comprehension. They occur when ice dams, holding back glacial lakes, suddenly fail, releasing the entire lake contents in a matter of hours or days. The channeled scablands of eastern Washington state were created by such megafloods. During the last ice age, a glacial lake called Lake Missoula formed in western Montana, held back by an ice dam. When the dam failed, the entire lake, 500 cubic miles of water, drained in about 2 days. The flood carved deep channels through basalt bedrock, created waterfalls larger than Niagara, moved house-sized boulders, and stripped away soil and sediment down to bare rock. These floods happened repeatedly. Each time the ice dam reformed, the lake refilled, then the dam failed again. Perhaps 40 times over a period of a few thousand years. The landscape today still bears the scars. Similar megafloods occurred in Siberia, in Central Asia, and elsewhere during the ice ages. They're rare events. Most rivers never experience them, but they demonstrate the extreme power of flowing water when enough of it moves fast enough. River capture. Sometimes rivers steal each other's water. This process, called river capture or stream piracy, happens when a river eroding headward cuts through a drainage divide and captures the flow of a river on the other side. Imagine two rivers flowing in parallel valleys, separated by a ridge. One river is eroding its valley more quickly than the other, perhaps because it has a steeper gradient. It cuts back through the ridge, separating the valleys. Suddenly, the other river finds a new, shorter path to base level. It abandons its old channel and flows through the gap into the faster eroding river. The captured river's flow is diverted. Its former channel downstream of the capture point is left dry, a beheaded stream with only local tributaries feeding it. Meanwhile, the capturing river gains additional discharge, which increases its erosive power, allowing it to cut down faster. River capture rearranges drainage patterns, sometimes dramatically. It can explain oddly shaped watersheds where a river seems to make inexplicable turns. It's a reminder that watersheds are not permanent features. They evolve over geological time, just as rivers themselves do. For most of Earth's history, base level has been relatively stable. Sea level fluctuates with ice ages, falling when ice sheets grow, rising when they melt. But these changes are measured in hundreds of feet, occurring over tens of thousands of years. Rivers can adjust to these changes. But what if base level changed dramatically and permanently? What if sea level dropped thousands of feet and stayed low, or rose thousands of feet and stayed high? This has happened in Earth's past, during rare supercontinental configurations. When all continents are merged into one supercontinent, the ocean basins expand to accommodate the displaced water, and sea level falls. When supercontinents break apart, creating new ocean basins, sea level can rise. A major drop in base level would cause rivers to cut deep canyons as they adjusted to the new lower base level. Rivers crossing continental shelves would extend their channels across what was formerly seafloor. A major rise in base level would drown river valleys, creating deep estuaries. Rivers would deposit sediment in their drowned valleys, filling them over time. These base level changes occur over tens of millions of years, giving rivers ample time to adjust. But the adjustments can fundamentally reshape continental landscapes. We've traced the evolution of rivers over geological time, millions of years without a single human presence. But humans have lived along rivers for our entire existence as a species. And in the last few thousand years, since we developed agriculture and civilization, our relationship with rivers has become profound and complex. Let's briefly consider this relationship, because it helps us understand both rivers and ourselves. The earliest human civilizations arose in river valleys. The Tigris and Euphrates in Mesopotamia, the Nile in Egypt, the Indus in Pakistan, the Yellow River in China. This isn't coincidence. Rivers provided water for drinking and irrigation. They provided fish and waterfowl for food. They provided transportation routes for trade. And crucially, they provided fertile soil on their floodplains, renewed annually by flooding. Ancient farmers learned to work with river rhythms. They planted crops in the rich mud left by floods. They dug irrigation canals to carry water to fields beyond the floodplain. They built levees to protect their settlements from the highest floods. These early agricultural societies developed along mature rivers with extensive floodplains, precisely the rivers we've been describing in the later stages of development. The characteristics that make a river geologically mature, gentle gradient, broad floodplain, regular flooding, are the same characteristics that make it valuable for agriculture. Ancient peoples developed intimate knowledge of their rivers. They could predict floods by observing upstream weather, by noting the water color, by seeing how high the river rose on marker stones. This knowledge was crucial for survival. Planting too early or too late, or being unprepared for a major flood, could mean starvation. The ancient Egyptians were masters of river prediction. They observed that the Nile's annual flood coincided with the heliacal rising of the star, Sirius, the first appearance of Sirius at dawn, after a period when it was too close to the sun to see. This astronomical observation allowed them to predict the flood weeks in advance. They also developed the Nilometer, a marked column or staircase that measured the flood height. Records were kept for centuries. A low flood meant drought and famine. A very high flood meant destruction. An ideal flood, about 16 cubits on the Nilometer, meant abundance. This kind of detailed observation represents early scientific understanding of rivers, even though it wasn't framed in modern scientific terms. People were observing, recording, predicting the foundations of hydrology. Humans didn't just observe rivers, we modified them. We've been doing this for thousands of years, but the scale has increased dramatically in the modern era. We dam rivers to create reservoirs for water storage and hydroelectric power. There are now tens of thousands of large dams worldwide. Some create reservoirs hundreds of miles long, drowning entire river valleys. We straighten rivers to make more land available for agriculture and to prevent flooding. Meanders that took thousands of years to form are cut off with canals, shortening the river's length and steepening its gradient. We build levees to confine floods, sometimes raising the levees higher than the surrounding landscape. The Mississippi River at New Orleans flows several feet higher than parts of the city, held back only by engineered levees. We dredge rivers to maintain navigation channels. We divert water for irrigation, sometimes taking so much that rivers run dry before reaching the sea. These modifications have consequences. Dams trap sediment, starving deltas of the material they need to build upward and outward. Levees prevent natural floodplain deposition, and the floodplain subsides without regular sediment input. Straightened rivers flow faster, causing increased erosion downstream. We're learning, slowly, that rivers are complex systems. Modifying one aspect affects others. The mature river we described earlier, with its meanders and floodplain and natural rhythms, is a system in equilibrium. Alter one component, and the whole system adjusts, though not always in the ways we expect or desire. Looking forward, rivers face new challenges. Climate change is altering precipitation patterns, making some regions wetter and others drier. Glaciers that feed many rivers are melting, first increasing river flow, then decreasing it as the glaciers disappear entirely. Rising sea levels are pushing saltwater further upstream in tidal rivers, threatening freshwater ecosystems and freshwater supplies for coastal cities. Yet rivers will persist. They're fundamental expressions of how water and gravity interact on a planet's surface. As long as Earth has an atmosphere, oceans, precipitation, and exposed land with topographic relief, there will be rivers. The specific rivers will change. The Mississippi might shift course, as it has many times in the past. The Amazon might grow or shrink, depending on climate patterns. New rivers might form in newly deglaciated areas. Old rivers might dry up if their source regions become more arid. But the processes will continue. Erosion, transport, deposition. The shaping of landscapes by flowing water. The patient, persistent, unstoppable work of rivers. We've followed a river from its birth on bare rock to its old age as a delta-building system. We've seen how water, given enough time, can reshape entire continents. We've watched landscapes evolve over millions of years, each stage flowing naturally into the next. A river is many things. It's a geological agent, carving valleys and building plains. It's a physical system, responding to gravity and the properties of flowing water. It's an ecosystem, supporting countless forms of life. It's a resource, used by humans for water, transportation, and power. But perhaps most fundamentally, a river is a story. A story written in landscape. A story that takes millions of years to tell. A story that's still being written even now. Every river on Earth is at some stage of this story. Some are young, cutting steep valleys through mountain ranges. Some are mature, meandering across broad floodplains. Some are old, building deltas at the coast. And all of them are changing, always changing, though so slowly that we barely notice in our brief human lifetimes. There's a paradox at the heart of rivers. They seem permanent. We name them, map them, treat them as fixed features of the landscape. But they're not permanent. They're constantly changing, flowing, reshaping their channels and valleys. A river is never the same twice. The ancient Greek philosopher Heraclitus observed this 2,500 years ago. No man ever steps in the same river twice, for it's not the same river, and he's not the same man. The water flowing past is always new water. The sediment on the bed has been reworked. The banks have eroded slightly. The channel has shifted, perhaps imperceptibly, but it has shifted. Yet there's also constancy. Rivers follow predictable patterns. Young rivers have steep gradients and V-shaped valleys. Mature rivers meander. Old rivers build deltas. These patterns repeat on rivers around the world, on Earth, and even on other worlds. They're expressions of fundamental physical principles. So rivers are both constant and changing, both permanent and ephemeral. They exist in the tension between these opposites. The story of rivers is ultimately the story of water's power. Not the dramatic power of floods and waterfalls, though those are impressive, but the quiet, persistent power of water flowing downhill, day after day, year after year, millennium after millennium. A single water droplet has no power, but trillions upon trillions of droplets, flowing together, can carve the Grand Canyon, can wear down mountain ranges, can reshape continents. This is perhaps the most important lesson from studying rivers. Given enough time, gentle, persistent forces can accomplish what violent forces cannot. Water doesn't attack rock. It simply flows over it, around it, through it. And slowly, patiently, inevitably, the rock yields. There's something almost meditative about this, something calming. The river doesn't hurry, it doesn't struggle. It simply flows, following the path of least resistance, doing its work without effort or urgency. Humans are newcomers to the river story. Rivers have been shaping Earth's surface for 4 billion years. Our species has existed for perhaps 300,000 years. Our civilizations for perhaps 10,000 years. We're a brief chapter, maybe only a paragraph, in the river's long story. Yet, we've had disproportionate impact. We've changed rivers more in the last 200 years than they changed in the previous million. Our dams, levees, diversions, and pollution have fundamentally altered river systems worldwide. We're part of the story now, for better or worse. We have the power to modify rivers, but we're only beginning to understand the consequences. We're learning that rivers are not simply resources to exploit, but complex systems that provide services we depend on. Water purification, flood mitigation, sediment transport, habitat for species we value. Perhaps the wisest approach is to work with rivers rather than against them. To understand their rhythms and processes, to allow them space to meander and flood when necessary, to recognize that they're ancient entities with their own logic, their own patterns, their own ways of being. In 1 billion years, if Earth is still habitable, there will still be rivers. They might flow through landscapes utterly different from today's. The continents will have moved. New mountain ranges will have risen and been eroded away. Old rivers will be gone. New rivers will have formed. But the fundamental processes will be the same. Water will evaporate from the ocean, fall as rain on high ground, flow downhill under gravity, erode rock, transport sediment, build deltas. The cycle we've described, the story we've told, will continue. In that sense, rivers are as close to eternal as anything on this planet can be. Not any individual river, but the process of river formation, the phenomenon of flowing water shaping landscape, that will persist as long as Earth has water and an atmosphere and exposed land. And so we end where we began, with water flowing across rock. Simple, fundamental, beautiful in its simplicity. A river is time made visible. It's erosion we can see, change we can measure, geological process happening before our eyes. Though we must be patient, must learn to see change that happens over years and decades and centuries. Watch a river, really watch it. See how it flows around obstacles. See how it deposits sediment on the inside of curves. See how it undercuts the outer banks. See how it rises with rain and falls with drought. See how it carries the story of its entire watershed, of all the land it drains, in the sediment it carries, and the water it bears to the sea. Every river is unique, yet every river is following the same ancient patterns. Every river is telling the same story in its own voice. The story of water shaping Earth, the story of change and constancy, of power and patience, of time beyond human comprehension. Rest now. Let the image of flowing water carry you to sleep. The river flows on whether we watch or not. The river flows on whether we sleep or wake. The river flows on through night and day, through seasons and centuries, through ages beyond counting. Always flowing, always changing, always the same. Sleep well.